this video, we'll be going over the component and projection of one vector onto another vector. The component of vector A onto vector B is the length of the shadow cast by vector A onto vector B. So the component is a length. It's actually the length of the adjacent side of the right triangle formed between the two vectors. So remember the definition of cosine. Cosine of theta, where theta is an angle between two segments, is equal to the adjacent side length over the length of the hypotenuse. So in this case, what we're calling the component is the length of the adjacent side, and the length of the vector itself is the length of the hypotenuse. So cosine of theta equals the component divided by the length of vector A. If I multiply both sides by the length of vector A, then that gives me a solution for the component of vector A onto vector B. So the length of vector A, the vector you're projecting, times cosine of the angle in between the two vectors is what we call the component. And again, it's the length of the shadow that is cast if you imagine the vector projecting onto another vector. Let us do an example. Why don't we find the component of vector 4, 2 onto vector 6, 1? First, we want to find the angle between the vectors. We could do this in several ways. One very direct way is to just look at each vector, find the angle each one is making from the positive x-axis, and then take the difference between those two angles. So for example, if I take inverse tangent of 1 over 6, that will give me the angle that vector 6, 1 is making with the positive x-axis, and it's approximately 9.462 degrees. If I take inverse tangent of 2 over 4, that will give me the angle that vector 4, 2 is making with the positive x-axis. If I take 26.565, which is the angle 4, 2 makes with the positive x-axis, minus 9.462, I get an angle difference of 17.103 degrees. So the angle in between those two vectors is 17.103 degrees. All I did was use the right triangle that is formed by each vector to find the angle each vector makes with the positive x-axis, and then I subtracted those two to find the angle in between. We also are going to need to know the length of the vector we are projecting. We're projecting 4, 2 onto 6, 1. So the length of a vector is really just an application of the Pythagorean theorem. The length of the vector is the hypotenuse of the right triangle formed by the x component and the y component. So for 4, 2, the length will be the square root of 4 squared plus 2 squared, or the square root of 20. Now that I know that, from our discussion earlier, cosine of the angle in between, so cosine of 17.103 degrees, is equal to our component length divided by the length of the vector 4, 2. So we're dividing by the square root of 20. So the square root of 20 multiplying cosine of 17.103 degrees will give us a length of 4.274. That is the length of sort of the shadow cast by vector 4, 2 onto vector 6, 1. That is what we call the component of 4, 2 onto 6, 1. It is the length 4.274. By the way, there is a formula for the angle between two vectors. If you're finding the angle between two vectors, you're always finding the difference between their individual angles measured from the positive x-axis. Remember that you can always find the x and y components of any vector by taking its length and multiplying by cosine of the angle measured from the positive x-axis to get the x component, and that length multiplying sine of the angle measured from the positive x-axis to get the y component. So I have two generic vectors written in that form. Take the dot product then of these two generic vectors. And so you get a cosine theta times b cosine beta added to a sine theta, b sine beta. Again, I'm doing the dot product, multiply the x components, add to the y components multiplied. If I then take that expression and I divide by the length a times b, I end up with the formula for the cosine of the difference between two angles. So cosine of the angle between two vectors is equal to the dot product of their unit vectors. That's what we have in the lower right-hand corner of our slide. Cosine of beta minus theta is the angle between the two vectors. It's equal to the dot product of the vectors, but then divided by each of their lengths. That's equivalent to the dot product of their unit vectors. So applying that formula to the example we were just looking at, if I wanted to find the angle between vector 4, 2 and 6, 1, I could find the dot product of their unit vectors. The length of 4, 2 we already discussed is the square root of 20. The length of the vector 6, 1 is the square root of 36 plus 1, or the square root of 37. So the unit vector for 4, 2 is 4 divided by the square root of 20, 2 divided by the square root of 20, and the unit vector for 6, 1 is 6 divided by the square root of 37, 1 divided by the square root of 37. Take that dot product and you end up with 26 over the square root of 740. So again, what occurred there, I'm multiplying the x's, so 4 times 6 is 24. And the denominator will be the square root of 20 times the square root of 37. And then you add the product of the y's, so 2 times 1 is 2, so 24 plus 2 is where the 26 came from. And if you take 20 times 37, you get 740. So the dot product of the unit vectors is 26 over the square root of 740. Cosine of the angle we're looking for is equal to that number. So inverse cosine of that number should give us our angle. And if you have your calculator in degree mode, because here we're listing the angles in degrees, and you take inverse cosine of 26 over the square root of 740, you get the 17.103 degrees that we calculated earlier. So by the way, we could also rewrite our formula for component. Earlier we discussed that the component is the adjacent side of this right triangle, and so its length is equal to the length of the hypotenuse, which is the length of the vector projecting the length of A, times cosine of the angle in between the two vectors. We just discussed that cosine of the angle between the two vectors is equal to the dot product of their unit vectors. So if I take length A and I multiply by the dot product of the unit vectors, the lengths of A cancel out. And so a common formula that you will see in a trig book or a physics book or any book that's working with vectors is that the component of A onto B is equivalent to the dot product of the vectors divided by the length of B. Again, when you set up how to calculate component, the length of A cancels out. So again, you'll see this formula. The component of A onto B is equal to the dot product of vectors AB divided by the length of B. B is the vector that you're projecting onto. You can extend the idea of component even when the vectors point in opposite directions. Here we have negative 4, 2 projecting onto 6, 1. But from the picture, we can see that it really doesn't look like I can project negative 4, 2 onto 6, 1. I can project negative 4, 2 onto the line containing 6, 1. And that is what we actually are doing when we interpret a component where the vectors are pointing in opposite directions. And we will denote the length of the component as a negative value, the negative indicating that the vectors are pointing in opposite directions. From there, the concept is no different. You do the same operations. I mean, you could see from the picture, you're finding the adjacent side of a right triangle. So I need to find the correct angle. In this case, it's 36.028 degrees. I could find that angle by individually finding the angles that the two vectors are making with the x-axis. In the case of negative 4, 2, you're making that angle with the negative x-axis. And because the line containing 6, 1 is below the negative x-axis, you end up adding the two angles together to get the angle in the right triangle that we're interested in, or follow the idea that cosine of the angle in between is equal to the dot product of the unit vectors. You're going to get that 36.028 degree angle either way. And then from there, you're still going to find the length of that adjacent side. And so it'll be the square root of 20 times cosine of 36.028, which gives us 3.617, but denote it as a negative value because the vectors point in the opposite direction. Or if you follow the formula we talked about a few slides earlier, that the component is equal to the dot product divided by the length of the vector you're projecting onto, you also get the negative 3.617. Okay, so the projection of vector A onto vector B is the shadow cast by vector A onto vector B, but now represented as a vector with length and direction. The component is just the length of that adjacent side of the right triangle. The projection is now taking that length and making it a vector. So if you found the component, then multiply by the unit vector in the direction of B. Again, you're projecting onto B, and you will then have that length turned into a vector. You could also follow formulas. We already talked about how the component of A onto B is equal to the length of A times cosine of the angle in between. That will be a number, a length. You're then multiplying that by the unit vector in the direction of B. We also learned that cosine of the angle in between is equal to the dot product of their unit vectors. So if you plug that in, again, the lengths of A cancel out, and you will then have the component length multiplying the unit vector in the direction of B. But when you do that, notice in the denominator are two lengths of B being multiplied, so the length of B squared. So a common formula for projection is the one that we have in the bottom right-hand side of this slide. It's the dot product of the vectors divided by the square of the length of B. That will be a value, a scalar value. You're then multiplying that by vector B. They're the same thing, okay? At the bottom right is no different than the formula in the middle of the slide. So you're taking the component length and you're multiplying by the unit vector in the direction of B. It's just when you clean that up, it turns into the formula that's in the bottom right-hand corner of this slide. So following that advice for the example that we did earlier, our component was 4.274. If I multiply that by the unit vector in the direction of B, I'm projecting onto 6, 1. So I'm multiplying 4.274 by the unit vector in the direction of 6, 1. And I will end up with the vector 4.216 for the x and 0.703 for the y. I also could just follow the formula that I had written on the bottom right hand of the previous slide and notice that we get the same vector. So vector 4.216 for x, 0.703 for y is a vector that is pointing in the same direction as 6,1, but has length that is equal to the shadow that vector 4,2 would cast onto 6,1. You can use the same idea for projection even when the vectors point in opposite directions. Our earlier example had negative 4,2 projecting onto 6,1. Our component was negative 3.617. So if you multiply that component by the unit vector in the direction of 6,1, you obtain the vector negative 3.568, comma, negative 0.595. Those are the x and y components of our projection. They make sense. You can see that the projection is in the quadrant 3 where x and y are both negative. I could also follow that formula where you dot the two vectors, divide by the square of the length of the one you're projecting onto, and then multiply that value by the vector you're projecting onto. Notice we end up with the same projection vector. So there's the definition of component and projection. The definition was presented in a couple different ways that are equivalent. You probably should be aware of thinking through both ways. I know if you're doing a lot of heavy physics, having these formulas for component and projection handy right on the tip of your memory is helpful. In the background though, I would make sure I understood that it's really just right triangle trig. You're just using things you already learned back in the right triangle trig section. All right, well, good luck with all of your practice.